Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It's my great pleasure to welcome SOUMALYA JOARDAR from Kolkata. It's actually really nice because if you look at this person in red in this lecture room, my student Atul, he's my current PhD student, and his supervisor in India was exactly Professor JOARDAR. So this is a kind of happy reunion. And topic is very dear to our hearts, equivariant C correspondence. SOUMALYA, it's all yours, take it away.
Thanks, Professor Hack. So let's begin. So as you can see, the title of my talk is Equivariant C correspondence. So the equivariance is actually with respect to compact quantum group action. So we have to introduce what is a C correspondence and what is a compact quantum group. To start with, ideally, I would have liked to give some motivation behind this work. This talk is actually based on a joint work with Dr. Subhrajit Bhattacharjee, but let me introduce these things first. Of course, both C correspondence and compact quantum group are well known to the audience today, but for the sake of completeness, let's introduce them nonetheless. So what is a C correspondence? So very naively, C correspondence is just a data that can produce C algebra, very naively. And historically, C correspondences were introduced to get graph C algebra and cross product C algebra both under one umbrella. So let us define what a C correspondence is. So as I said, C correspondence is just a data. What is that data? The data is actually a triple a C correspondence, a right Hilbert module epsilon over a unital C algebra A, and a unital C homomorphism from the C algebra A to the C algebra of all adjointable operators on the right Hilbert module epsilon.
So I have a question already there.
Yeah.
Go ahead.
This is something like a self correspondence, yes, from A to A, yes.
From A to
It's
A,
like
what?
A by module, yes. In general,
Yeah,
you can have correspondence from A to B, yes.
Right. A by module, but it is slightly more general than that, I guess. You can view this phi giving a left module structure sort of, because if I mean this unital system homomorphism from A to adjointables on E will give you a left A module structure in some sense. So it's
yes, but
like
the algebra is only one algebra A. It's
yeah,
always
it's only one algebra A.
So
yeah,
in this
it's
sense,
only one
it's like
algebra.
an endomorphism, yes.
Right. Okay, so as I was saying, so the C correspondence is just a data. So let us give one quick example of a C correspondence. The most important example for this talk is a C correspondence arising from finite directed graph without sources. So this finite is rather a technical assumption to ensure that the corresponding graph sister algebra. So as I said, a C correspondence gives rise to C algebras. So this C correspondence coming from finite directed graph will produce graph C algebra, and we assume the directed graph to be finite because we want unital graph C algebra. That's all. So for our purpose,
wait. Sorry, wait. Yes. To have unital graph C algebras, it just suffices to assume that the set of vertices is finite. You might have infinitely many edges.
Right, and finite means set of vertices are finite. Finite graph will mean.
But so why do we assume that you have finitely many edges? You don't need it for unitality.
Right. So for us, finite directed graph will mean that the number of vertices is actually finite.
Okay, but you don't care about the edges. Okay, so that's...
I don't care about the edges.
But that's confusing. I mean, this is really confusing because whenever you say finite directed graph, you surely need that both sets are finite, E1 and E0. So that's confusing terminology.
Okay. So that's the terminology may be confusing, but by finite directed graph, I would mean that the number of vertices are finite.
Okay, great.
Okay. then if we are given such a finite directed graph, and without source is another technical assumption really. So suppose we are given a finite directed graph without sources, then the function over the edge space, that's a vector space, finite dimensional vector space. If on the top of it you assume that the number of edges are also finite, that also perhaps needed that the number of edges is finite, then the function space over edges that has a right Hilbert E0 module structure. E0 is the function algebra over vertices. So what is the right Hilbert module structure? This xi, that's an element which is really a function on the edge space. So a function on the vertex set, it can act on right. It can act from right on this C1. How does it act? It acts via this range map. So sorry. So this is the, okay, so it's still not working. Okay, no problem. So this is the range map. So the graph comes with a source map and a range map. So every edge has this range and source, both are vertices. So using the range map, one can define the right Hilbert module structure. And this adjoint,
I'm not sure, but I think that your psi and eta should lie in C of. I'm a little bit confused. You have
this xi is a function on edge. Yeah, this xi is a function on edge. So xi dot f, that's a module action. That should be a function on edge set, right? So it should take an input edge. E is an edge. So xi evaluated at D, that gives a complex number, and f is a function on the set of vertices. So if you take the edge R of E, range of that edge is another vertex. So f evaluated at that vertex makes sense.
Okay, that's right.
And this is just multiplication between complex numbers. Okay, so it is again a function on edge space. Okay, and and this is the inner product that makes it a right Hilbert sister module. Okay. Again, the inner product actually uses the range map again. So the source map will play a role to define this phi. Remember, sister correspondence is a triple. So we have this right Hilbert module, this epsilon A. Epsilon is the function space over edges. This sister algebra A is actually function algebra over vertices. And right module structure we have using the range map. And now this phi, which should be a unital system homomorphism from the function algebra over vertices to adjoint table of this module CE1, that is where the source map will play the role. So yeah, so where is the phi map? Here is the phi map. You can see phi f, that should be an adjoint table operator on C of E1. So it takes a function which is xi, and this E is again an edge. So if it is evaluated at source of P, and this is again a complex number, and xi evaluated at the edge E, this is another complex number, so it's again a complex number. So this phi, so using the source maps, you can give that unital sister homomorphism phi from the sister algebra of vertices to adjoint table over the function space of edges. This is one example. Yeah.
Just let me make sure I understand it. I can write on your screen. So here I understand that you mean it with these parentheses, right? I mean, phi of f is now an adjointable operator, so it acts on this element, but this is again a function, so you evaluate.
Right. Right,
But I'm
right.
confused about these parentheses because I understand that psi of E is just a number. So why would you put parentheses over a complex number?
No, we don't really need any parentheses here. I think we don't need
Okay,
it.
okay.
These two
Thank
are just complex numbers, multiplication between complex numbers. So we really don't
Okay.
need parentheses.
Okay, because
Okay,
that's
so-
confusing because it looks like it's a function of something. No, but it's
Right.
just
I understand. That's confusing because those two are just complex numbers, so we don't need parentheses. So, yeah, so this is the most important example for our talk. So there is another example which is not that important, but a little bit important. So let's give that example
Can-
as well. So
Can I ask a question also here?
Go
yeah,
ahead.
sure.
Hi. So
Just
C of
switch the
E-
camera on, please.
Okay, if I manage. See. Okay.
Much better.
So E0 vertices are finite. That's it. What you said. It's
Yes.
finite vector space. Okay.
Mhm.
E1 is finite or not? I didn't got
E1
it.
is finite because we need a finitely
Okay.
generated projective module later on. So let's assume that E1 is also finite.
Okay, so all these are kind of matrices, yeah, because so all these modules are actually Hilbert spaces at the end, finite
Right.
dimensional, and all
Not Hilbert
operators are
spaces, not Hilbert spaces, because your module is over C of V0. So that's the
finite
functional
dimensional
algebra.
Hilbert modules are Hilbert spaces after all, no, at the end. Or maybe I'm mistaken. So perhaps.
Yeah, sorry, I could not hear you. Sorry.
So all finite dimensional Hilbert modules are, maybe not over the C. Okay, over C are Hilbert space.
Over
Okay, sorry. Okay, but all operators are adjointable in your case because of
right,
finite
all
dimension.
operators are adjointable. Yes,
Okay,
yes.
thank you. Okay,
Sure.
bye-bye.
Sure.
Thanks.
So that will play also a role that all operators are adjointable actually. Yeah, so again, coming back to the second example. So suppose we have a sister algebra admitting a circle action, then this is standard that an element is called homogeneous of degree n if we have this condition, this gamma z, this is the action of circle on the sister algebra C is equal to Zn times A. Again, this is just complex number Z power n. So now if we denote the linear space of elements of degree n by Cn, then the fixed point subalgebra C0, you can see if C0 is nothing but gamma Z acting on A is nothing but equal to A. So that's the fixed point subalgebra of the original sister algebra C. So this C1, which is the spectral subspace corresponding to n equal to 1, that's a Hilbert sister module over this fixed point subalgebra. And the structure is again inherited from the original sister algebra C. So you can figure out the structure. It's not that difficult. All the structures are essentially inherited from the original sister algebra. So that becomes a sister correspondence. So again, this phi is given by this map. Phi A acting on Xi is nothing but A times Xi. So you can see both A and Xi, they belong to the original sister algebra C. So you have the multiplication within the original sister algebra. So that again becomes a sister correspondence.
But,
So
you don't have to choose C1. You can choose any Cn.
Any Cn, right? You can choose any Cn actually. Then this becomes, yeah, so C0 if you multiply, I think you can choose any Cn.
Yeah.
Yeah. So these are sort of technical things like sister correspondence is said to be finitely generated projective if the module is finitely generated projective, and it is said to be full if the span of the inner product is actually dense in the sister algebra A. And for the purpose of this talk, all the Hilbert modules will be finitely generated and projective. That's the standing assumption. That makes a compromise, I understand, but for our purpose, it will suffice. The assumption will suffice. And the main example is anyway comes from finite directed graph. So the module is actually a finite dimensional vector space if we assume the set of edges to be finite. And So as I said, in the example coming from finite rejected graph without sources, the C-star correspondence is full and finitely generated. And in the second example, the C-star correspondence is full and finitely generated, provided we have that the circle action is principal, and principal in the sense that you have CN, this thing should be C of M plus N. That if the circle action is principal, then the C-star correspondence will be full and finitely generated.
Just let me quickly comment. So what is guaranteed by the very concept of an action is that this is contained. Okay.
Yeah, this is contained. Yeah.
So that's true just because you have a circle action.
Circle
but
action,
actually,
right?
the equality, so containing the other way around, this is tantamount to freeness of your action, or if you want principality. Yeah.
Right. And
I have a question. I'm really puzzled. Could you give at least a slight hint of why you don't like sources? What's wrong if we have sources? Typically, people avoid sinks. So, are you using this opposite convention, like Ian Rayburn, or do you really mean sources? And if you really mean sources, why?
Do we need the sources? I think sources by source we mean that without source means that any vertex, all the vertices receive at least one edge, right? That's the standard. That's the standard. That is what we assume, I think, but I don't really recall where exactly it is needed.
So let me ask you this question. If you look at this graph, that's for you the Teplitz C-star algebra?
Sorry, if I look at this graph, then?
Yeah, you look at the C-star algebra of this graph. Okay. So if you have the convention, A, then this is the Teplitz algebra. But you also have the opposite convention, where you have just interchanging of the concept of range and source, and when the Teplitz algebra is given with an edge ending in here. So the best way to establish which convention you are talking about is whether or not, when you look at this, is like the simplest non-trivial graphs. Okay, is it the Teplitz algebra or is it not?
Sorry, what is it?
Is it the Teplitz algebra?
Oh, Teplitz algebra, you are saying? Yeah. So I think it is a Teplitz algebra. So that will mean that we are having with a graph without sources, right?
No.
The usual convention, right?
Yeah, I'm just trying to figure out which convention you mean. If you use an old convention, then this graph with an edge outgoing, that's the graph of the Teplitz algebra. And if you can confirm it, then I know that you're using old convention. If you are using a new convention, then this arrow has to point in the other direction.
So I am without source will mean that what I assume that every vertex should receive at least one edge.
But that wasn't my question. My question was, is this equality true in your convention? Is the C-star algebra of this graph the Teplitz algebra? The universal C-star
the C-star algebra
of
this graph is Teplitz algebra. I think so. Okay. So should I continue?
Yeah. Sorry.
No problem. So when the module is finitely generated and projective, then the C-star algebra of compact operators that coincides with the full C-star algebra of all adjointable operators, and in particular it is unital. The C-star algebra of compact operators on this right Hilbert module generally plays a role in the definition of the Pimsner algebra, which are C-star algebras arising from C-star correspondence. But since we are assuming finitely generated projective, so it really won't play any role, because this anyway coincides with the whole the full C-star algebra of all adjointable operators on this Hilbert module. So now, if we have a C-star correspondence, then we can talk about representation of the C-star correspondence on a sister algebra. So remember, we shall generate a sister algebra out of a sister correspondence. The way to generate is to look at certain representation of sister correspondence on sister algebras. So a representation, what is a representation? So a representation of a sister correspondence on a unital sister algebra. So that's a pair T pi, let's say. So pi is a unital sister homomorphism from A to B, and a linear map T from the right Hilbert module epsilon to B, such that these are sort of obvious conditions. So you have to have compatibility. So these are just compatibility. And anyway, so one would expect that one should also assume T of xi dot A should be T xi into pi A, but that can be proved that it is actually sort of automatic. It follows from these two conditions. So, and if we are given such a representation, then there is a well-defined system homomorphism. One can prove that there is a well-defined system homomorphism psi t from the sister algebra of compact operators on epsilon to B, such that on this sort of rank 1 operators, this thing actually holds. Psi t of theta xi eta is t xi t eta star for xi eta in the Hilbert module epsilon. And not only that, moreover, we have the expected sort of compatibility with this unital with this not unital, sorry, with the sister homomorphism psi t and the representation t and pi. And again, when epsilon is finitely generated projective, as we know, this sister algebra of all compact operators on this Hilbert module epsilon is nothing but the sister algebra of all adjointable operators on the Hilbert module. Then this psi t is actually a unital sister homomorphism from LE to B. So this is a representation of a sister correspondence on a unital sister algebra. But to get the Pimsner algebra, we need a little more. We are interested in not any representation, but a little restrictive class, what are known as covariant representation of a sister correspondence on a sister algebra. So what is a covariant representation? So roughly it has to do with what are known as Katsura ideal. So let us briefly recall what a Katsura ideal is. So a Katsura ideal is actually intersection of kernel phi part with phi inverse of all compacts. Okay, so you can phi in general is a map from the sister algebra A to all adjointables. So we have to restrict our attention to phi inverse of Ke. But in our case, you can see the Katsura ideal actually reduces to kernel phi part, because if epsilon is finitely generated and projective, this Ke, the sister algebra of all compact operators on E, that coincides with LE. So phi inverse of LE, that that becomes redundant actually. So this the whole sister algebra A intersection kernel phi part. And if phi is also injective, then kernel phi part will be 0. So this Katsura ideal actually doesn't matter in that case, but we allow phi to be non-injective as well. So for us, the Katsura ideal is just kernel of phi part if our sister correspondence is finitely generated and projective. So what is a covariant representation? So covariant representation of a sister correspondence is, first of all, that's a representation of a sister correspondence on a sister algebra B. So it will be given by a pair T pi, and it is said to be covariant if psi t of pi A equal to pi A for all A in the Katsura ideal. You can see psi t is a priori defined on Ke. So necessarily you have to restrict your attention A such that phi of A belongs to the compact operators on the Hilbert module E. But again, for our purpose, since we are assuming our Hilbert module to be finitely generated projective, this A actually belongs to only kernel phi part. So the Katsura ideal actually reduces to kernel phi part. So now we can.
Could you remind me, please, the definition of this psi t?
Yeah, psi t.
It's from the previous slide. Yes, I'm sorry. Didn't
The
memorize.
Psi-T is a map from the sister algebra of all compact operators. So in particular, take a look at this rank 1 operators, theta, xi, eta. You take this rank 1 operators, so Psi-T will act on this rank 1 operator. It will produce an element of the sister algebra B. So it will be given by T xi, T eta star.
Okay, I
So
see.
T is the representation of the sister correspondence. So T xi,
Yes.
T eta both will belong to
Yes.
the sister algebra B.
Yes, okay.
Yeah, so that's the covariant representation of a sister correspondence on a sister algebra. So now we can define the Pimsner algebra. So what is the Pimsner algebra associated to a sister correspondence? The Pimsner algebra, associated to a sister correspondence is the universal sister algebra admitting a universal covariant representation of the sister correspondence. So one can actually produce a concrete realization of the Pimsner algebra into represent on some operators on Fock spaces, but we shall not really go into the concrete representation. We shall be happy with this sort of abstract definition of a Pimsner algebra, and this universal property will be crucially used to prove certain things. So again, so we shall since the Pimsner algebra, since the sister correspondence also has a covariant representation on the Pimsner algebra by definition, so it has a universal covariant representation, and we shall denote the universal covariant representation by the pair Ke Ka. Ke is the linear map from E to OE, and Ka is the sister homomorphism from A to OE. So these are all notations really. So let us give examples of Pimsner algebra. So again, like I said, the most important example is the example coming from finite directed graph. So if we consider finite directed graph again without sources, then the corresponding Pimsner algebra will be isomorphic to the graph sister algebra. And what are the universal covariant representation of the sister correspondence in the graph sister algebra? They are again given by Ke delta E. Delta E is the linear basis of CE1, the function space over edges. So that's a finite dimensional vector space. So Ke delta E will be the generating partial isometries, and Ke delta V will be the projections corresponding to the vertices. And recall the second example of sister correspondence coming from a sister algebra admitting a, let's say, principal circle action. Then the corresponding Pimsner algebra is isomorphic to the original sister algebra that we started with. Okay, so these are two main examples of Pimsner algebra arising from sister correspondences. And again, using the universal property, one can show that there is a canonical circle action on Pimsner algebra, which extends the covariant representation in the following sense, that Kza, if you take the sister algebra A, so the circle really doesn't act very trivially there, and Kz xi is nothing but z times xi for all z in the circle. And in the example of the graph sister algebra, this circle action is nothing but the usual canonical circle action on the graph sister algebra. And in the second example, the canonical circle action is the original circle action that we started with. Okay, so this circle action on the graph sister algebra will again be important in a moment. So that's a quick overview of Pimsner sister correspondence and the Pimsner algebra. So now let us give a very quick overview of compact quantum groups. So what are compact quantum groups? I think this is fairly well known to the audience. Again, let us very quickly recall what are compact quantum groups. The compact quantum groups is actually a pair where this pair CG delta, where CG is actually unital sister algebra, and this delta is a unital sister homomorphism, which is actually co-associative. Co-associative means that identity tensor delta composed delta is nothing but delta tensor identity composed delta. And we have this by simplifiability or the cancellation property, whatever you like to call them.
Or
And
freeness of an action.
or freeness of an action, whatever you want to call them. So now some standard facts about compact quantum groups. So a compact quantum group admits a unique bi-invariant state called the Hart state. And what do you mean by bi-invariant? Bi-invariant is this condition H tensor identity compose delta Q equal to identity tensor H compose delta Q is equal to H Q1. So this is again just quantum analog of the existence of Hermiter on groups. And some more standard facts. So if we are given a compact quantum group G, then there is a dense star algebra CG such that that dense star algebra becomes a Hofstadter algebra if you restrict our co-product delta to this star subalgebra. And there is a natural co-unit and antipode. And Hart state.
Sorry, but you miss a word here. There is.
Yes, sorry. Which word?
You miss a word here. Moreover, there is a co-unit.
No, there is a co-unit. That's a typo. Yeah. So there is a co-unit and then antipode. So that makes it a Hofstadter algebra.
Why do you denote the antipode by kappa?
That's Voronovich notation.
Okay. This was original, yes, notation?
Yes,
well, original is Hopf, and Hopf wouldn't denote it by kappa. But when Voronovich discovered compact quantum groups, his convention for the antipode was kappa.
Okay. I'm asking because I'm used to using S for
S is the standard notation.
Okay.
S for antipode. So so the Hart state is actually tracial on this dense Hofstadter algebra, but it is in general not tracial on the whole sister algebra CG. But when it is tracial, then the corresponding compact quantum group is called a Koch type compact quantum group, and there are equivalent conditions. The equivalent conditions that you can say that this kappa squared is identity, or all the Bernoulli functionals are actually trivial. They are equivalent conditions for a compact quantum group to be of Koch type.
Sorry, but I think this is wrong. I mean, H is not tracial on this Hopf algebra. I mean, you don't have, even when you restrict yourself to this dense subalgebra, it is not true that H of AB is equal to H of BA in general. Take the Hopf algebra of SQ2 and take its car measure, and this is just not true, even if you restrict yourself to the Hopf algebra. So what you mean is that the Hart state H is faithful on C of G. That's true, not tracial.
Oh, faithful, not tracial. Right.
This is very wrong. This is very wrong.
This is wrong. This is not tracial. This is faithful on this dense Hofstadter algebra. This is wrong. Right. So yes. So compact quantum, that point. So let us come to the actions of compact quantum groups. So what do we mean by an action of a compact quantum group on a unital sister algebra A? So that's actually a unital sister homomorphism alpha from A to A tensor CG, such that these are again, straightforward generalization, the quantum analogs of classical group action on spaces. You can say this is the Podles condition, and this is sort of the co-associativity condition. And again, like in the we could prove the existence of a dense Hofstadter algebra, one can prove, given an action of a compact quantum group on a unital sister algebra, one can prove the existence of a dense star subalgebra A naught of A, such that this alpha is actually algebraic over A, meaning that this alpha of A0, this image lies in this algebraic tensor product A0 tensor this dense Hofstadter algebra CG, and moreover for all A in the dense star subalgebra, this condition actually holds. Identity tensor epsilon alpha A is actually equal to A, and this action is said to be faithful, or the CQG G is said to act faithfully on A if this omega tensor identity alpha A. If omega is a functional or linear functional on A, then this is dense in CG. So we'll be interested in typically faithful actions of CQG. And this is a terminology. So if CQG G acts on a sister algebra A, then A is said to be a G sister algebra. So this terminology will be helpful to state.
Okay, no. Could you please go back to the previous slide? Let's analyze a little bit. So first, please allow me to comment. This is a very, very interesting condition, and I think you didn't mention it, but maybe not everybody realizes it immediately. But actually, what this condition means is that when you have, so imagine that you have a group acting on a space, okay? So when you have a group acting on a space, one of the things that you want is that you act on any element with a neutral element of a group, then it just acts by identity.
It fixes, it fixes. So this is the quantum analog identity tensor epsilon alpha A.
Exactly. And somehow there are some compact quantum group sister algebras that are simple, so there is no co-unit map. Okay, so this is why Podlesh. By the way, you have a spelling mistake here. Podlesh spells
yes. So I could not find it.
Okay, so this is quite fascinating. It's a beautiful exercise to prove that if A is commutative and G is classical, then it's indeed tantamount to just this simple condition. And that's this subalgebra, which is denoted by A0, that's what we call the Peter-Weil comodule subalgebra. And yes, it has lots of nice properties. It has actually, two definitions. One which was originally given by Podlesh, and one which was given by us later on. And they are equivalent under the additional assumption which we like to make, which assumes simply that the coaction is injective. Okay, that's a non-trivial assumption because you see, of course, whenever you have, say, a co-unit, then injectivity is immediate. It follows from this condition, okay? But in general, this condition doesn't hold on the sister level because there's no co-unit on the
whole quantum group, So
and using some crazy things with norms, you can construct counterexamples. You can construct coactions. You can construct things that satisfy these two conditions, but this alpha is not injective. So when we assume injectivity, then our definition of this, basically our definition is like yours, right? I mean, we assume that this is a subalgebra, sort of the biggest subalgebra, over which it is a comodule algebra over this cobalgebra. I mean, you can make it rigorous, but whereas with Podlesh, I forgot actually his definition, but they differ if this action is not injective. And there is a nice paper of Piotr Sołtan in which he proves that they differ precisely by the kernel of alpha. So if
kernel of alpha,
they are identical. And could you tell me, because I'm a bit confused here, so if G is classical and A is commutative, so what is this faithfulness? What does this faithfulness mean?
If G is classical
and A is commutative, so you have just
group action on space. I understand.
So what does it mean?
Group action. So this density. I don't know. I haven't thought about it. So you have any guess? I mean.
Well, I think it means that the group action on the space is faithful, right? That is
what do you mean by
no, I don't believe it.
Faithful.
No. Transitive means that coaction invariant subalgebra is trivial. That's transitivity. No, this is definitely not transitivity.
Not transitivity.
This essentially.
I don't know. So any guess? But I could not guess. Also, I mean,
what means that okay, you don't have a smaller
subgroup acting on that space, maybe.
Yeah, that is. I think that's what
I think that.
I mean, that is precisely by the density condition. That's what I think. The whole group, in a sense, is acting, not a subgroup.
Okay, let's make a very simple exercise. So in particular, omega can be a character. If A is commutative, right, then omega can be a character. So it's
Character,
given
right.
by a point X in your space X of which the group X.
Mhm.
And what you are talking about here is that when you take a function and you run your X with a fixed G, then you get all possible functions. So sort of something like this. You have a function on X. You have a function on X, okay, and you fix your G. Am I right?
Are you
Yes.
fixing your
No.
G, or you're fixing a point in the space?
No,
Because
wait a second.
you're fixing a point in the
space.
space, I think.
Because
So
this guy, sorry, this guy now, when you have an omega, this guy is a function on G. Okay, sorry. So this is like this. You have okay, and now this is a function on G. This becomes a function on G.
Function on G, yes.
Yes. And now you are saying that all functions on G are basically of that form.
Hmm.
What does it mean? So if you are to get all functions, then in particular you cannot have that. Okay, so but it's kind of. Because you must, but then you take all x's. Okay.
You are varying your x's, yeah. We are varying your x's over the space.
So okay, so I think I've got it now. It means that if for all x, x of g is equal to x of g prime, then g is equal to g prime. But for all x, so it's not freeness condition, okay?
No, not free.
Yeah, it just means that if for all x's action agrees, okay, so basically it means that you have a faithful representation of G in the homeomorphism group, automorphism group of X. Okay, so here's the faithfulness. We solved the problem. Okay.
Okay. Yes, I think.
Yeah.
Yeah. So let's continue. So let's quickly give some examples of CQ reactions. So this is very standard examples. Suppose you are you have a set with only finitely many points n, then your sister algebra Cx is just the universal sister algebra generated by n commuting mutually orthogonal projections adding up to constant function 1, and the quantum permutation group Sn plus actually acts on the sister algebra Cx. So this is very standard by now. And what is the quantum permutation group? We have to specify what is the underlying sister algebra and what is the coproduct. So the underlying sister algebra is the universal sister algebra generated by n square elements Qij, such that all Qij's are projection. And you have this is called, if you look at the matrix formed by Qij, this n by n matrix is actually magic. That's the condition. This is known to everybody, I think. And the coproduct is the standard coproduct given by delta of Qij equal to summation Qik tensor Qkj. And this Qij you can think of a quantum permutation. So if you like a permutation which can take the vertex I to j, so quantum analog of that, roughly you can think of. And so we have to specify what is the corresponding action on Cx. The action is given by alpha pj. Remember, the sister algebra Cx is generated by all such pj's, is nothing but summation pi tensor Qij. And so remember our sister correspondence, the main example of sister correspondence was the sister correspondence coming from finite directed graph. So suppose you are given a finite directed graph, then the finite directed graph has a quantum automorphism group, and it has actually two versions. One is due to Banica and one is due to Julian Bischoff. By now it is more standard to take the version of Banica, simply because Banika's quantum automorphism group a priori is a larger quantum automorphism group that can coact on a graph. So what is this quantum automorphism group of a graph in the sense of Banika? This is actually the quotient, the underlying sister algebra is nothing but the quotient of CSN plus, which was the sister algebra of the quantum permutation group, by this ideal, Voronozh ideal, you can say, dictated by this commutation relation UD minus DU. U is the n by n matrix Qij, the fundamental unitary matrix of the quantum permutation group, and D is the adjacency matrix of the graph. So this is again very, straightforward generalization. You can think of it as a straightforward generalization of the classical case. You can, you can define the classical automorphism group by this prescription as well. All you have to, impose the condition of commutativity among all the quantum permutations Qij. Again, the coproduct is given on Qij by the same formula. This is summation k Qik tensor Q Kj. And what is the coaction of alpha? And so this is sort of, we have to understand the action. By action, we mean an action on a sister algebra, typically on a unital sister algebra of a compact quantum group. So what is the underlying unital sister algebra? This is the sister algebra of continuous functions on the set of vertices. So this action is given on the set of vertices by this, again, by the same formula as it was given for the case of finitely many points. So to work in the compact quantum group category also, this finite directed graph is sort of important. Otherwise, we don't have the sister algebra of continuous function of vertices. We don't have unital sister algebra. So really, we cannot really work in the category of compact quantum groups and unital sister algebras. And another very standard example of compact quantum group action is the action of the quantum unitary group on the Kunz algebra. So let us recall what is a Kunz algebra. This is again sort of going to be a little important. So the Kunz algebra is the universal sister algebra generated by n isometries satisfying this condition, the summation I si star equal to 1, and the quantum unitary group Un plus can act on Kunz algebra. So what is a quantum unitary group? You can, again, think of it as almost like a unitary group, but we don't have the commutativity among the generators. So what is the underlying sister algebra of this quantum unitary group Un plus? Is the universal sister algebra generated by n square elements Qij such that both the matrices Qij and Qij transpose Qji, they are unitaries. Again, the coproduct is given by the same formula, and the action is given by alpha of Sg equal to Si tensor Qij. So these are very standard and well known. And by the way, the Kunz algebra also admits action of AUQ, not only Un plus, AUQ. What are AUQ? So AUQ again generated by n square elements such that this Qij matrix is unitary, but the transpose is no longer unitary. It is almost unitary, but this is twisted by an invertible matrix Q. That's where the role of Q comes, AUQ. And it is important that this Sn plus or this quantum automorphism group of a finite graph or this quantum unitary group Un plus, they both are compact quantum group of Koch type. But this AUQ, when Q is an invertible matrix, which is not identity, it is no longer Koch type. So it is again sort of going to be important shortly. So now I can sort of give the motivation behind the work. So what we observed previously, that suppose we are given, not only us actually, also some other mathematicians like Simon Smith, Maurice Weber, they also independently observed this thing, that if you are given a finite directed graph G, then the corresponding quantum automorphism group of G in the sense of Banika, this actually also acts on the corresponding graph sister algebra. So, and one can actually specify the action of the quantum automorphism group of the graph on the graph sister algebra. This is given by alpha S equal to summation F SF, F belonging to the edges. So remember, so if you are given a graph, the generating partial isometries are corresponding to the edges actually. So alpha S equal to SF tensor Q source F source C Q RF RE. So then, and by looking at the C-star correspondence arising from graph, so this quantum automorphism group, we had an intuition that this quantum automorphism group of graph might be actually some quantum symmetry of the underlying C-star correspondence. That was our guess. So for that, we have to really define what is a quantum symmetry of C-star correspondence. So that we shall define. And then, since the quantum automorphism group is actually a quantum symmetry of the C-star corresponding arising from the graph structure, then if we can prove that any quantum symmetry of C-star correspondence naturally leads to an action on the corresponding Pimsner algebra, so that will sort of explain this phenomena that quantum automorphism group of the underlying graph automatically leads to, as an action on that corresponding graph C-star algebra.
Can I ask
Yes,
again?
sure.
So before we go to correspondences, we have just the C-star algebra of a graph. So you said that quantum automorphisms of graph act on C-star algebra of the graph. Are they quantum automorphisms of the graph algebra?
Yeah, graph C-star algebra.
There is also notion of quantum automorphisms of a C-star algebra.
Quantum automorphism of
Swami, Bauming, all these people, other people. Can you assure that this is
so quantum automorphism
you
of
just say
graph
that
C-star algebra?
yes. Is it a quantum automorphism of a graph C-star algebra or
So I'm not aware of
wait,
that.
wait. May I answer, Ludwig? Sorry.
Yes. Okay.
Let me, if you don't mind, let me try to answer. I think that what SOUMALYA has in mind here is that you have your graph, and given a graph, you construct a certain automorphism quantum group, compact quantum group. Okay,
Yes.
you have a C-star or compact quantum group, and then you also have a graph C-star algebra of this graph. And I understand the first point, please correct me if I'm wrong, in the sense that you take this compact quantum group generated directly by the graph, and then in some natural, if not canonical manner, you can define a coaction of this compact quantum group on this
the graph C-star algebra.
And that's it. That's all that it says. But you no longer can claim, Ludwig, the problem what you're saying was the following is that when you look at the graph, you define this compact quantum group as the automorphism group. I mean, there is something behind calling it the automorphism group.
The automorphism group, yeah.
The complete automorphism group. But you can no longer use the word automorphism group. It's just a group acting, it's just a compact quantum group acting on a C-star algebra. You just have a coaction, but it doesn't have any universal property.
Universal thing, right?
Okay.
Exactly.
Okay.
So in general,
Okay.
if you are given a graph C-star algebra, in general, it's difficult to get a universal object, universal compact quantum group acting on graph C-star algebra. You have to assume some state preserving on something like that to have a universal object.
Okay, maybe I just take this opportunity. I think that this faithfulness we mentioned before means that in the classical case, it's just the action is effective. Maybe that's the...
Yes, maybe this is called, yes.
Okay.
Yeah.
Okay.
Yeah.
Bye-bye. Thanks.
Yeah.
Okay. Yeah, so that brings to the concept of quantum symmetry of C-star correspondence, or equivalently we call equivariant C-star correspondence. So suppose we start with a compact quantum group and a C-star correspondence epsilon a phi, let's say, such that the C-star algebra A is actually a G C-star algebra, meaning that the compact quantum group G has an action on the C-star algebra A. Then a G equivariant Hilbert A module is a pair epsilon lambda, let's say. So epsilon is a right Hilbert A module, let's say, and our C-star algebra A, that's a G C-star algebra. then a G equivariant Hilbert module A is a pair epsilon lambda such that there is a linear map lambda from this Hilbert module epsilon to epsilon tensor CG such that these natural conditions hold. These are very natural. So if you have lambda acting on xi dot A, this is the module structure. This should be lambda xi alpha A. So alpha is the action of the quantum group G on the sister algebra A, and you have this compatibility of the inner product, very natural, and you have this co-associativity and this again natural density condition. So, and with very similar argument that is used to prove in general the existence of a dense unital star subalgebra given action over which the action is actually algebraic, one can prove a dense subspace epsilon naught of the Hilbert module epsilon such that the linear map lambda, which we would like to call as an action, is actually algebraic. And then we can define what are equivariant sister correspondences. So suppose we are given a sister correspondence, that means a triple epsilon A phi, then it will be called a G equivariant if A alpha is a G sister algebra, epsilon lambda is a G equivalent Hilbert module, so this should be really epsilon. This is not E, and we have this natural compatibility with this map phi lambda phi A acting on xi. This should be phi tensor identity alpha A acting on lambda xi.
I have a question.
Go ahead.
So in the previous slide, can you go back?
Yes, sure.
So what tensor product are you considering? Epsilon tensor CG?
So this is the exterior tensor product. So you can consider your CG as a Hilbert module over itself because it's a sister algebra. Then you can think of it as an exterior tensor product between these Hilbert modules.
Okay. So you're thinking that as a right model.
A tensor Q module, A tensor CG module.
Right. Okay. Yeah. Thanks.
Okay. And any sister correspondence is automatically circle equivariant. This is sort of already covered in a sense that we have already mentioned that any sister correspondence admits a circle action, automatically admits a circle action. And given a sister correspondence, the n-fold interior tensor product is naturally another sister correspondence over A if we take the interior tensor product. And one can show that given a G equivariant sister correspondence, the sister correspondence obtained by taking interior tensor product is also G equivariant. Now
there is a question in the chat. Wait, there's a question in the chat. Weber and Schmidt. Wait a second. I'm trying to read it. Okay. Weber and Schmidt showed. This shows that the quantum symmetry of a graph coincides with the quantum symmetry of the graph C-algebra. Had a quick scan of a paper and
I understand.
Sure what state on graph we are preserving. Apologies, not in a position to unmute. Okay, so all right, this is a very interesting comment. Yeah, thank you so much. Yes.
Yeah, so I understand that. So the thing is that I also had a look at the paper when we were working in these things. So the thing in that paper, so what do you mean by quantum symmetry of graph structure? That's the first point. So that should be some universal compact quantum group acting on the graph system algebra in some sense. Now, it depends on what category you are working with, right?
Exactly.
And the category will also include the action, right? So it turns out that in that paper, the action has a very special form. It's not any general action. It has a very special form, as far as I remember from that paper. So that special form makes the quantum automorphism of the underlying graph to be the universal object in that category. Okay. Now, if you relax that special form of the action was precisely of this form, alpha AC equal to SF tensor Q, something like that. Okay, so I don't, I mean, completely recall the paper, but as far as I understood, because you can see, even if you assume a linear action, let's say, on the Kunz algebra. Kunz algebra is a graph system algebra. If you assume that you have a linear action of a compact quantum group on a graph system algebra, meaning that, so it would have been better if I could write. Yeah, so
May I ask you a question about this formula, because it's puzzling me, you know, this formula.
this formula,
Yeah, exactly.
Yeah.
So imagine that your graph is just a Kunz graph. So you have one vertex and say
no. There is a problem with the graph of the Kunz algebra, because in order to define quantum automorphism of a finite directed graph, you have to assume that the graph doesn't admit multiple edges.
Okay.
Because even if you want to define classical automorphism group, if the graph has more than one edge, more than one edge between two vertices, then it's a problematic thing, right? You cannot really define the classical, even the classical automorphism group. So you want to permute two vertices, then you don't know, and consider one edge, then you don't know where to send that edge, right? Because you have more than one option. So you have to assume that the graph doesn't have any multiple edge. Okay. Yeah, so coming back to the example of the Kunz algebra. So let's say you want to consider this kind of linear action, right? Of compact quantum groups. Right? Then this is very easy to see that the category of all compact quantum groups, such that the compact quantum group has a linear action like this, it doesn't admit any universal object, right? Because any AUQ can act in this way on the Kunz algebra. Right? So again, as I said, it depends on what category we are working with to talk about universal object or quantum symmetry of graph system algebra. It turns out that their category is in some sense very algebraic and a little bit restrictive. But if you want to work in a category like all CQGs acting linearly, in that sense that it preserves the set of the generating partial isometries, then if you don't assume any state preserving property, then you cannot really expect the universal object to exist in that category. It is far too general. Okay, I hope I am clear. Yeah. So should I continue now?
I'm also having the problem with the multiplication here.
Which multiplication?
I don't see how. Here you multiply elements in the compact quantum group sister algebra, right? And multiplication is not an algebra homomorphism. So I'm somehow how do you prove that this alpha is really a coaction? You know, that alpha, that if you iterate a coaction here, you put alpha, or you put identity and coproduct here, but you get the same. I'm somehow, maybe I'm wrong, but I'm really scared of multiplication here.
Yeah, so you can try to see that the you can try to use the universal property of graph system algebra, I think. That because there are lots of relations in among QIJs, if these QIJs are coming from quantum automorphism group of the underlying graph. Okay, so that's long tedious calculation. So you can look at there are few papers, I think Simon Smith and Morijo, they also do the calculation. You can look up that paper also, or you can look at the paper by myself and Arnab Mondal on quantum symmetry of graph sister algebra related things, like 1 or 2 papers are there. So one of them should contain this calculation, how this is actually a well-defined sister homomorphism on the graph sister algebra. And also why this is co-associative and all. Okay, so this is a long tedious calculation. You have to keep track of a lot of things. So that was one of the main motivations to I mean, we are sort of thinking, is it an accident that this is happening? Like, because of there are some tedious calculation, you can do the calculation and see that this is indeed a coaction, or there is a more, in a sense, more fundamental reason behind it. So the quote unquote the more fundamental reason that turned out to be true is that this quantum automorphism of graph, the quantum automorphism of the finite directed graph is actually quantum symmetry of the sister correspondence coming from the graph, and in turn that actually tells you that the quantum automorphism of the graph will give you a coaction on the corresponding Pimsner algebra, which is the graph sister algebra. Okay. Yeah. So now this is the main theorem. And suppose you are given a compact quantum group and a G equivariant sister correspondence over the G sister algebra A alpha. Again, where our standing assumption is that the sister correspondence is finitely generated and projective. Then there is a well-defined unital sister homomorphism omega from the Pimsner algebra to the Pimsner algebra tensor CG, making the Pimsner algebra a G sister algebra. Again, this is really not new because this was already available in the literature, and I mean, in a sense, in a more general setting, that you don't really need to assume your module to be finitely generated projective, and you don't have to assume that your compact quantum group, your quantum group is actually compact. You can work with Hopf sister algebra category, and you can drop the finitely generated projective assumption. Then also you have a well-defined unital system homomorphism, making it a G sister algebra. But we worked in the category of finitely generated projective sister correspondence, and there is a trade-off. What is the trade-off? So if you drop the finitely generated projective condition from your sister correspondence, then you have to add the weak invariance of Katsura ideal. So I won't go into detail what do we mean by some the weak invariance of Katsura ideal under the suitable actions on the Hilbert module and the underlying sister algebra, the sister correspondence. But if we work with this finitely generated projective sister correspondence, then the invariance of Katsura ideal is automatic. You don't really have to assume the invariance of the Katsura ideal.
Sorry, can we go back to the main theorem? Because I have a serious problem with your conclusion. You see, for me, it's vacuous because there is always a well-defined unital sister homomorphism. Take any unital sister algebra A and take any compact quantum group G. Then, of course, you always have a map which just maps A into A tensor 1. And of course, it's a coaction and it's unital and everything. So I think this claim is doesn't make sense.
Right. I understand your point.
It's always true for any sister algebra. So you have to see what kind of well-defined. What kind of
What kind of sister homomorphism is we are having? That's the point. I think I understand your point. So these are the again.
You should write the formula and say, when the following formula,
this formula,
blah, 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 a G sister algebra.
So this is the formula.
Exactly, yes. So that's your theorem.
I understand your point. Of course, you can always cheat and say that there is always this coaction, but this formula actually, the crux of the main theorem is that this formula actually works.
Yeah.
Yeah, and again, the proof is actually using the universal property of defining universal property of the sister of the Pimsner algebra. So recall the universal covariant representation of the sister correspondence on the Pimsner algebra. Then one can show that these natural maps, they are actually this pair T pi. This is actually a covariant representation on the sister algebra OE tensor CG. Then by the universal property, there is a well-defined sister homomorphism from OE to OE tensor CG such that this thing holds. This comes from the universal property. And as I said, this main theorem actually appeared in the literature before in a slightly different setup. And if you drop the finitely generated condition, then you have to throw in the weak invariance of the Katsura ideal condition. And if you assume the finitely generated projective condition, then you don't need the weak invariance of the Katsura ideal. It is sort of automatic. And in fact, we prove a little more. You don't really have to go to the so this is the invariance condition of the Katsura ideal, but I mean, you expect that this should hold for A belonging to the Katsura ideal, but what we could prove that you don't really have to assume A belonging to the Katsura ideal. For any A in the sister algebra, the coefficient sister algebra A of the sister correspondence, this equality actually holds. Psi t of phi A is actually equal to phi A. So this is sort of trade-off. Yes. Now, one can ask the following question. So, when is a CQG action a lift? What do we mean by that? Suppose G has an action on a Pimsner algebra OE. So it has an underlying sister correspondence.
Could you please go back to the full screen?
Yeah, but in the full screen I cannot write. Okay, fine,
Okay.
no problem. Yeah.
Okay.
No problem. Yeah. So let us stick to the full screen. So the question is, when is a CQG action lift? So what do we mean by that? Suppose G has an action on the Pimsner algebra, and then is the underlying sister correspondence is G equivariant, so that the lifted action omega in that form, as Professor Hag was mentioning, in that particular form coincides with the original action. So it turns out we can give a quick necessary condition for the positive answer to the above question. The necessary condition is the original action on the Pimsner algebra has to be the circle action equivariant. So remember, the Pimsner algebra always admits a canonical circle action. So the necessary condition for an action to be a lift in that sense is that it has to be circle equivariant. But in general, this is not sufficient, as we can see from a quick example. So take Kuhn's algebra for example. So Kuhn's algebra comes from a sister correspondence, and you can easily see that the Hilbert module of the sister correspondence is nothing but an n-dimensional Hilbert space over complex number, because you have only one vertex. So your sister algebra is complex number, so your Hilbert module becomes a Hilbert space, n-dimensional Hilbert space. So and it is very clear that for any action of any compact quantum group on Kuhn's algebra, if it has to be a lift of the corresponding action on the sister correspondence, it has to preserve the span of SI, right? Span of generating isometries, because the action should come from the action on the corresponding H space. So H space will correspond to the generating partial isometries. So it has to preserve the generating partial isometries. But one can easily produce this action rho SI, which is SI tensor 1 U, where U is this unitary. So this is no longer a linear action in the sense that it doesn't preserve this span of SI. So this action cannot be a lift of the any action any action on the underlying sister correspondence. And it turns out that this circle equivalence condition will be both necessary and sufficient for the Pimsner algebra coming from a principal T-sister algebra. And it is not really unexpected, because this is how the Pimsner algebra coming from a principal T-sister algebra is built. So this is sort of more of a side note. So let us come back to this OT plus G, the quantum automorphism group of G. So this was our motivating example in some sense. So as I mentioned, so one can show that if we have a finite directed graph without sources, then this OT plus G, the quantum automorphism, then if you consider this OT plus G, which is the quantum automorphism group of the graph G, then the sister correspondence coming from the directed graph G is automatically OT plus G equivariant. This is what we expected.
Wait, and now you don't assume anything about your graph. It's absolutely arbitrary graph.
Directed. No, still I'm assuming finite directed and without multiple edge, because these are necessary to define
your theorem. I mean, you should write your theorem.
Right. Maybe I should write this in the theorem, because to define OT plus G, this is necessary. Because if we don't have finite directed graph without multiple edge, then actually we don't have this OT plus G.
I mean, you're missing a preamble, like saying let G be a finite directed graph, blah 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 blah. Then the sister correspondence.
Then the sister correspondence coming from the directed graph is OT plus G equivariant, and consequently there is an action of OT plus G on the graph sister algebra sister G, thanks to our main theorem. So this is how we recovered the action of OT plus G on sister G. So as I said, in particular, this will give us a more sound understanding. In some sense, it depends on what do you mean by more sound understanding. And there's another important observation that we observed earlier, that not in this talk, I mean in an earlier work. Suppose G is a graph such that the corresponding graph sister algebra admits a KM state at the critical inverse temperature. Okay, and the KM state with respect to the canonical dynamics of the graph sister algebra coming from the circle action. Then OT plus G, which is the quantum automorphism group of G, then it preserves the KM state if and only if it preserves the restriction of the KM state on the commutative sister algebra CE0. Again, whenever we are writing OT plus G, that will always mean we are assuming that our graph is finite directed and without multiple edge, because otherwise we cannot really define OT plus G. So this was another observation which was sort of an accident. So we had to compute and really show that if the quantum automorphism group of the underlying graph, it preserves the KM state on the graph sister algebra if and only if it preserves the restriction of the KM state on the commutative sister algebra CE0. That's the sister algebra on vertices.
So
again,
could you comment how strong is this assumption of admitting a KMS state?
So this is I think fairly strong assumption that admitting a KMS state at critical inverse temperature. Okay, so it has so it has I mean if you have a KMS state at the critical inverse temperature, so if you restrict the KMS state, that will be an n tuple of and that is an element of Cn, right? If your graph has n vertices, right? So there are n many projections, you can restrict them, so you get a vector basically, right? So that vector has to be an eigenvector of the vertex matrix corresponding, the eigenvalue is related to the critical inverse temperature actually.
And could you state some simple sufficient condition for a sister algebra, graph sister algebra to admit this KMS state?
Yes. So I don't remember whether there are other technical assumptions, but as far as I remember, if you look at the vertex matrix, but of course, when there are restrictions, when you can have an eigenvalue, I think the eigenvalue related to the critical inverse temperature. The eigenvalue has to be of a particular form, then you are looking at the eigenvector corresponding to the eigenvalue. Yes, that is what I remember. So you can consult. I mean, there are some papers in the reference I will mention. You can consult those papers for more information about KMS states on graph system algebra. Okay, so this is critical inverse temperature. You can consider existence of KMS states beyond critical inverse temperature, less than KMS inverse temperature, and the critical inverse temperature. So you can consult those papers. Yeah, so as I was saying, so we sort of discovered it that this OT plus G automatically preserves the KMS state if and only if it preserves the restriction of the KMS state on the commutative sister algebra CE0. Again, we thought that this might be related to the sister correspondence coming from the underlying graph structure, and it turns out to be true. So let us recall very briefly some facts about KMS states on the Pevsner algebra. So again, the KMS states on the Pevsner algebras are considered with respect to quasi-free dynamics, and the quasi-free dynamics is actually dictated by the module dynamics. Okay, the Hilbert module related to the Hilbert module. If we have a module dynamics, then we have a quasi-free dynamics, then we can consider KMS states. And the module dynamics is actually given by a family of unitaries. UT, T is indexed by real number, and UT is belong to the sister algebra of adjoint table operators on the Hilbert module epsilon. And the generator is basically the usual generator, that's a unitary group. So you have a generator. So with respect to the above module dynamics, so under some more technical conditions, KMS states at a given temperature beta are in 1-1 correspondence with the tertial states on the coefficient sister algebra. Okay, and in case of the graph sister algebra, the usual KMS states are considered with respect to the trivial module dynamics, which will lead to the canonical circle action on graph sister algebras. And in that case, KMS states at a temperature beta are in 1-1 correspondence with states phi on CE0, because I mean tertial doesn't is vacuous for CE0 because CE0 is actually a commutative sister algebra. Now we can talk about invariance of KMS states again. So start with a Koch type CQG. This is important. You have to start with a Koch type CQG. Then the theorem says that if we have a G equivariant sister correspondence such that lambda, if you recall, G equivariance will include this data lambda, which is a linear map from epsilon to epsilon tensor CG. This commutes with D or equivalently commutes with the module dynamics UT. Then the lifted action omega. So whenever we have a G equivariant sister correspondence, then we have a lifted action omega. The lifted action omega on the Pevsner algebra preserves a KMS state if and only if it preserves the corresponding tertial state on the coefficient sister algebra here. Okay, this sort of looks very natural because we already assume that this lambda has compatibility of with the module dynamics, and the KMS state on Pevsner algebra is actually dictated by the module dynamics and the tertial states on the coefficient sister algebra. Here in the theorem, we are assuming that we have a G equivariant sister correspondence such that this lambda commutes with the module dynamics, and also this lifted action, also the action of the compact quantum group G on the sister algebra A, if it preserves the tertial state which will generate the KMS state. If it preserves the tertiary state, then the lifted action should preserve the KMS state. It looks very natural, but the thing is that it is not automatic. You have to assume that your compact quantum group is of Koch type. Okay.
Sorry, I'm really confused by this theorem. So you have a compact quantum group of Koch type, fine, everybody knows what it is. Then you have a G equivariant C correspondence, say you explained it, but I'm confused. What is lambda and D? So I'm given a G equivariant C correspondence. Could you please remind me what lambda and D stand for?
Yes, sure.
Lambda, I believe you use, but D, I'm completely unaware of what it is.
Yeah, so this lambda is this map.
Yes, okay.
Lambda is that map, okay?
Linear map.
Linear map, right, linear map, because you are assuming that your sister correspondence is G equivalent, right?
It's kind of faking a coaction, okay.
Yeah, faking a coaction, right? So, yes.
And what is D?
This D is the generator of the module dynamics.
Aha, okay.
So it looks almost
wait
natural.
Wait a second. Is it that you always have it? So I'm just given this G equivariant correspondence. So then I always have this. Is this family of unitaries uniquely given?
Family of unitaries is uniquely given. Yeah. So corresponding to a KMS state, you are given a family of unitaries, or equivalent if you are given a family of unitaries and you are given a tracial state on the coefficient sister algebra, then you can have a KMS state at a given temperature. So whenever we are talking about a KMS state, that means we are given a family of unitaries.
Yeah, but here in this first part of your theorem, you don't mention any KMS state. And if I understand you correctly, in order to have this D, this generator,
yeah, you need a KMS state. You're right. You need a KMS state to have a D. I mean, or the other way, whatever you like. But we're assuming that
your preamble is not complete. I mean, you should say the GBA Koch type,
right.
correspondence, and blah blah blah, be a KMS state on this.
Right, and D is the corresponding module dynamics. Corresponding to the KMS state.
Okay, thank you.
So yeah, then the lifted action preserves the KMS state if and only if it preserves the corresponding tracial state on the coefficient sister algebra. So it again, if you look at this quantum automorphism group of G and the graph sister algebra thing. So this odd plus G is Koch type CQG, and this module dynamics is trivial, meaning this is scalar dynamics. If you recall the circle action, then the circle action is comes from the trivial module dynamics. So this condition becomes vacuous, like this is automatically true. This linear map lambda will automatically commute with the module dynamics. Then since odd plus G is Koch type, then odd plus G will preserve the KMS state on the graph sister algebra if and only if it preserves the KMS state, if and only if it preserves the corresponding state on C0. That is what we observed previously, merely by calculating things. But here you can see that this is no accident. This comes from the sister correspondence. Yeah, so, and one cannot really avoid the Koch type condition, because if you drop the Koch type condition, then this is not always true, meaning that let us give you a quick example. Suppose you consider the Kunz algebra with n generators, again the usual example. Then you can see that this AUQ for any Q is actually is a quantum symmetry of the underlying sister correspondence of Kunz algebra, which is actually the module is actually n-dimensional Hilbert space and all, and the C of V is nothing but complex numbers. Then for any Q, AUQ doesn't preserve the KMS state. Okay, although it will trivially preserve any state on C, but it doesn't preserve the KMS state. So if it preserves the KMS state only when Q is identity, that is when we have the quantum unitary group. So one really cannot avoid the Kach type CQG condition. If you drop the Kach type, you cannot really hope to improve this theorem. That's what I mean. So yeah, so back to OT plus G. So again, let us fix a finite directed graph without source. Then,
by the way, your time is up, so please think of winding things up.
Yeah. So I can maybe go to the quick synopsis. So this is the point number one. Suppose we have a G equivariant finitely generated full sister correspondence, then there is a well-defined sister homomorphism, making this a G sister algebra. And for a Kach type CQG, the lifted action preserves a KMS beta state if and only if the action alpha preserves the corresponding tertiary state on the coefficient sister algebra under suitable condition. Of course, you have to put in the commutation with the module dynamics as well. And the sister correspondence arising from a finite directed graph G without sources is OT plus G equivariant, so that the OT plus G has a natural action on the graph sister algebra. And actually, OT plus G is realized as a universal object in a category closely related to the notion of G equivariant sister correspondence. It turns out that if you restrict our category of CQG acting on any sister correspondence, then we can actually get back our OT plus G as a universal object of that restricted category. Another very interesting application of all these things that I didn't have the time to discuss. Suppose we have a finite directed graph without source, such that the range map or the source map is 1, 1. Then the two notions of quantum automorphism group of a graph due to Banica and Bischoff, they actually coincide. So it's a nice condition because all you have to look at the graph and see whether your range map or source map is 1, 1. If one of them is 1, 1, then these two will coincide. And remember, Banica's quantum automorphism group a priori is a larger quantum automorphism group compared to Bischoff. And these are references. So so for KMS state on graph sister algebra or in general on Pearson algebra, one can consult this paper by Neshvev and Lakav. And Katsura's papers are standard references for sister correspondences, I guess. And how this OT plus G coacts on acts on the graph sister algebra. For that, one can consult this paper by myself and my co-author. And of course, for compact quantum group, the standard reference, I think, Vornovich's the original paper, compact matrix pseudo group. And this work is based on this archive paper, equivariant sister correspondence and compact quantum group action. Yeah.
Great. That's the end?
Yeah, that's the end. So because the time is up, I think.
Yeah, but I wanted to hear from you, but you're done. Okay, so thank you very much.
Thank you for inviting me.
Yeah, my pleasure. So let's start with questions. Any questions from Warsaw? No. Okay, any questions from Zoom? I don't see any raised hands, but
maybe I would like to ask one question.
Okay.
So, I'm familiar with these KMS states, but mainly in the context of von Neumann algebras, and this gives rise to many important invariants of von Neumann algebras. So, what is the significance of these KMS states in the context of general sister algebras?
Okay, so you mean the importance in terms of the structural property of sister algebras? So,
for example,
so I don't know. I have not seen any really application of KMS states in the structural property of sister algebra. Really.
Okay.
You mean that by looking at KM state, do we have some information of the original sister algebra, something like that?
Yes, since there
Yeah,
is
something in the-
some information about von Neumann algebra.
Yeah, right.
These
So,
KMS
but
states were used to define
right. So I'm not a specialist, so
invariance. Mhm.
so you can look up the literature or maybe ask any specialist. I'm not really a specialist, but I have not really seen anywhere that KM states are particularly used to get information about the sister algebra. It's more like most of the time this is introduced like this is just generalization of the Gibbs state on matrices.
I see. Okay, thank you.
Anybody else? Tomek? He's not answering. Okay, so I don't see any other questions, so let us thank our speaker again. Thank you again. Thank you.
Thanks.
Thank you.
Let me stop recording.